Hello everyone, I'm Guillaume Perez, and I'm going to talk about our paper Nonlinear Time Projection onto the L1 infinity ball. And that's a joint work with Laurent Condat and Michel Barlaud. So first, some motivation. We are all familiar with the data model prediction framework in machine learning where we have some data and we want to train a model such that with new data we will be able to make predictions. So this is like basic machine learning where in the middle we have a neural network here, like standard neural network. And so we are going to do our training. We're going to have like a large neural network and we will be able to do some inference. The thing is, in practice, often we have some constraints, which is like a fixed amount of memory that we can use. And the larger the network, the more memory you're going to use. And in addition, the more you have weights in the network, so the more you have neurons, the more you need computing power. So this is also something that we have. For example, in your computer, you have fixed amount of GPUs, and you can't exceed that. In addition, when you are working with device on the edge, for example, on your smartphone, you don't want to use all the energy of your smartphone just to see there's a cat in a picture. So you need to be careful with your model with these kind of things. And in the end, you have a fixed budget that you can't ignore in general when you are designing a device. So in the end, what we would like to do is to reduce all of this at the same time, like the memory, the compute power, the energy, but while keeping a decent network. Okay, and one method to do that is to use sparsity. So sparsity is like a very well-known topic from machine learning, and there is several ways, like many different ways to enforce sparsity in the model. And here I'm going to talk about some of them, and we're going to see what we're going to do with our projection later in our training. Okay. But first, what do we want to do with sparsity here? So, for example, what we could want is to remove neurons that we think are useless to make our predictions. For example, here, all the red neurons, we think they're useless. So we are going to design an algorithm detecting them and removing them such that we have a network which is way smaller, which is still able to make the prediction, but with less memory, computing power, energy, and that costs less in the end. And the thing is, that's great from this point of view, from a consuming point of view. But in addition, what we have and what we're going to see in our results is that most of the time when you are going to apply sparsity methods while training, you're going to obtain a model which is stronger and more robust, so potentially a higher accuracy in your predictions. So the question now is, how can I have sparsity in my model? So the different way to do sparsity selection, different kind of things in machine learning, there is a large state of the art of that. But for sparsity in particular, you can think of this problem here where you want to minimize a function f of x, where x is just going to be, a vector containing all the weights of the machine learning model that you are currently training, such that the L0 norm, so the number of non-zero entries on your vector, is bounded by epsilon. Okay, so epsilon is the number of non-zero entry that you are going to accept while training your model. Okay, so this is like the basic definition of sparsity. I want to minimize my model, so I want to optimize some loss function, but I don't want to have more than epsilon non-zero values in my weights. Okay. So this is basic definition, but the thing is, this is NP hard to solve because the L0 constraint is in the combinatorial constraint. But this is well-known fact, and since then we have a lot of relaxation. For example, for vectors, most of the time you can use a Q norm. For example, the Q equal 1 norm is the sum of the absolute value is just the LASO. Okay, so last method is like a well-known method for applying sparsity, but you could have also Q equal 2 for applying some regularization. So there's many different values of Q that you can use, and you are going to obtain different values, like different results in your optimization framework. I think here we are working with matrices. And for matrices, we can use different norms. For example, we could use PQ norms this time. Okay, so the PQ norm is based on the Q norm above. And a good thing is that with this kind of norms, we will be able to use the fact that we have a matrix and no longer a vector here. And again, just like for vectors, many different implementation of this framework have been done with P and Qs being different values. And in this presentation, we are going to focus on the L1 infinity ball. So that's a particular case where the infinity norm of a vector is simply the maximum value of this vector. And the main reason why we are going to use this norm is because in the general case where you are going to use a L1 something norm, then you will have structure sparsity. And structure sparsity is really great because you are going to have a faster processing and efficient presentation, all of that, because instead of removing just some values somewhere in the matrix, you will be able to remove complete column or rows of your matrix. So the resulting matrices are going to be smaller and faster to process. Okay. So we are talking about projection operation, and so the projection operation onto a constraint is an operation that take a point and find the closest point that satisfies the constraint. Okay, so that's the projection operation. And projected gradient descent is the algorithm that iterates between one gradient step and one projection step. Okay, so you don't need to know more about that. I mean, all of the projected gradient descent code are already online, and this is a well-known topic. But here we are going to talk about the algorithm for doing the projection onto the L1 infinity ball. So an algorithm that takes a matrix and project this matrix onto the L1 infinity ball given a radius. And there's many papers that have proposed algorithm for doing that back from 2009. And recently there have been several papers because this is a particularly useful norm because it induces structure sparsity. So we want to have fast algorithm to doing that. And the thing is, even if the recent papers, I mean, they are smart, they do some really interesting things, they don't really use the fact that we want to apply sparsity. So potentially the result is going to use and to have sparsity. And I'm going to talk a bit more about that later, but this is going to be the main point of this presentation, okay? So now for the rest of this presentation, I'm going to show you how the ICML09 from Quatoni's algorithm works. And this was the first algorithm defined for the L1 infinity projection. And then I'm going to show you several algorithmic tricks to improve this algorithm and for in the end make it the fastest algorithm, okay? Thanks to the four tricks that I am going to talk about. So Quatoni's algorithm is an algorithm that uses four steps, okay? And the first one is quite simple. So here you have a matrix, okay? So each column have a color and gradient of colors represent the higher the value and lower the value, like the gradient of values. And the first step is simply for each column to sort them. And the reason is that we need to sort them and then apply some linear algorithm, which is to do the cumulative sum of the sorted vector and things like that. Okay. But the main point is that we want to have them sorted. Okay. Okay. Complexity of sorting all the all the column of a matrix is m, because there is m columns, times n log n, like the cost of making a sort. Then the second step is once all of them have been sorted and we made the cumulative sum and apply some process, we want to have a global sort of these transform values. Okay, so this is just our matrix where we take all the values and sort them with respect to their values. And this is the second step. So far pretty basic. First step, sort the columns. And second step, once you apply your linear process, make again a sort, but this time of the complete matrix. And the complexity here is n times log mn, because this is just sorting n values. So before going to step 3, the main reason why we made the two first steps is to create this vector here, okay? Because in this vector, there is somewhere a threshold where using all the values before, we will be able to process the projection, okay? So the projection operation that we're going to do in the end is going to be a function of all of these values. And we want to find this threshold. And to do that, once we have the vector, in fact, we can just iterate until we find the threshold. Okay. So this is a simple process. In fact, this is a linear process. So here, the threshold is here. So in general, the complexity is going to be k, and k here is potentially n times m. It's the number of values that we're going to use for projection. Okay. And that's it. I mean, once you find the threshold in general, you're done. And the only thing that is remaining is to build the matrix, like the resulting matrix. So the last step of this algorithm is pretty simple. In fact, once we find the threshold, all the columns that have been fully consumed before are going to be set to 0, and the others are going to be bounded here. And this is the resulting matrix. So 0 here, 0 here, this column being removed, and these ones are being bounded. And that's it. The complexity of doing that is simply linear on, looking at the vector, and the global complexity is nm times log nm, which is the pre-process, in fact, of this algorithm, the step 2, which is to sort the complete matrix. And now, for the rest of this presentation, I'm going to show you 4 tricks to make this algorithm, which is currently orders of magnitude slower than the current algorithm, the new best when we have sparsity, just even 1% of sparsity or something. So first, the first trick. The first trick that we are going to see is to simply say, okay, once I have sorted all of my column, instead of building, the sorted vector, I am building a heap. So the complexity of doing that is mn log n, which is sorting each of the columns, and mn is the heapify function that makes a heap. So we did not yet use the heap, we just made the heap. And now now that the heap is done, the step 3 can simply be done by extracting the maximum value of my heap until the maximum value is the threshold value. Okay, so this is the same algorithm as before, except that instead of iterating over my vector, I am using the heap instead. So this is the exact same results. The main difference is that key times I have extracted the max to my heap, and the complexity of extracting the max is log mn. And the mn here at the end is just, creating the matrix back. So this means that the global complexity here is mn log n, so sorting the columns, plus k log mn. Okay, so this is the complexity. But the thing here is that we know that k, when there is a bit of sparsity, and most of the time, is going to be close to mn. Okay, so we did not really gain something here potentially. Okay, trick number 2. So this time the trick is pretty simple again. Instead of starting the algorithm by sorting each of the column, I am making a heap of each of them. Okay, the complexity here is linear because heapify is linear. And now that I have each of these small heap, instead of building a big heap, I can build a smaller heap that contains the maximum value of each of my columns. And this comes from the fact that since I am taking only the max of my heap, I don't need to have all the values of my column. I just need to have the maximum value that have not been yet extracted. Okay. And so the complexity here is m, because this is of size m, plus m log n, which is extracting the maximum value of each of my heaps. So now that all my local heaps, so one heap per column, have been made, and my global heap, just like for trick 1 is made, I can do the step 3. The main difference with the previous one is that here, each time I am going to remove the maximum. For example, if I remove this maximum value here, then I am going to replace it with the next maximum value from this column. And to do that, I am just going to call the heap here. Okay. So the algorithm is going to be as follow. The global heap is going to be extracting maximum value per maximum value to build, the threshold vector. And each time a value is removed from the global heap, the local heap is called. So this means that I am doing k is number of values here, k call to both the local and global heap. So this results in a complexity which is k log nm, which is the same, in fact, as the previous trick, okay? Because we know that k most of the time is going to be like really close to nm, so we have a global complexity of mn plus k log nm, okay? And that's great, but can we do better? Okay, let's continue. So now here the proposed algorithm. We call it reversed because we are going to work in a reverse order as the previous algorithms. So instead of iterating k times, to extract the k values between the threshold, we are working on the other part of the vector, okay? And we are going to do that in a lazy way. So instead of taking the maximum value, we are taking the smallest value and reversing the algorithm. So this means that the number of iteration on our algorithm is going to be something that we call j here, j, and the number of iteration of our whole process is going to be mn plus j log mn. So this is in fact exactly the same complexity of the trick true algorithm, except that we have j here instead of k. The thing is that j is equal to nm minus k, and k tends to be nm when we have a bit of sparsity. So this is why we've done this algorithm. And the paper is mostly the mathematical stuff to prove that we can find the threshold by working in the reverse order. Okay. So now look at the results. So to give you some sort of order of magnitudes, the proposed algorithms works several order of magnitudes faster than most of the existing algorithm, except for the other fastest one, which is 2, where we are only 2 to 3 times faster in general. Okay, so this is the precision times comparisons for matrix of size 1000, 10,000, and these kind of things. We made many different comparison. You can find them, all of them, in the paper. Okay, so in red, this is the sparsity. You see that even when there is a really low sparsity, then their exam is still faster. And since, and this is the most important fact, our algorithm, the complexity of our algorithm is a function of j, we try to plot j to give you an intuition. So when the sparsity is like really high, j is close to 0. But also, and that's like the most important thing, when the sparsity almost hits 0, and even 0, the sparsity is like the J value is around 5% and 2% of the matrix size. So the J value is always really small for this. So you can find all the code that we are using for this presentation, and all the tricks and everything you want, and also many different norms, projection, etc. In our GitHubs, up with the different papers. So in conclusion, gradient descent and norm projection, they are fast to compute. Some gradient descent is fast, and we saw how we can have fast projection, and they provide good sparsity. And by good sparsity, I mean either structure sparsity and better accuracy. So you can have all of that in the paper. And we proposed the nearly non-time projection operation with the good global complexity. And as you can check in our code, we use basic C++ implementation. So there is no hard-coded structures that you need to maintain where there could be bugs. And we also provide the C++ PyTorch implementation. So if you want to use that in your code, like in your machine learning pipeline, without losing performances. So if you have any questions, please feel free to send me an email. Thank you for listening to this presentation.